Good afternoon, everyone. So I think the sequencing has been done quite well. So after simple comes simple X and Mano, all the hand models and the whole body models with face and hands. So one of the original authors, Dimitris, I've known him for a long time. It's extremely good to work with. He's a professor at University of Amsterdam currently and winner of multiple awards. The most thing I liked about Dimitris is always he was the best reviewer for every conference I have seen. That's a very good learning. But without any delay, I'll hand it over to Dimitris. Thank you so much for accepting.
Thank you for the introduction. So welcome everyone and welcome to my talk titled Towards in the Wild Understanding of 3D Human Object Interactions. As humans, we live and move in a physical 3D world and we constantly interact with objects to perform tasks. And virtual 3D people, they need similar interaction capabilities for both perception, namely reconstruction from images, and synthesis in virtual worlds with virtual objects. And this looks like the following. We have this virtual avatar navigating within this virtual scene, grasping objects, manipulating them, preparing a drink, having a seat, and preparing to enjoy the drink. And when we look at this, the problem seems as if it has been solved, right? However, this is not the case. Actually, this is a reconstruction of myself in a high-end mock-up lab. This costed more than $1 million. And there are a lot of people behind the scenes, like cleaning the data and so on. So this is slow, expensive, and does not scale. Instead, we need to automate this with AI so that we reconstruct any interaction from images or synthesize any interaction with any object in any visual world and so on and so forth. And to this end, we meet a lot of challenges. First, 3D or 4D data is really scarce. But even if we had the data alone is not enough for a very simple reason. Our machine learning methods, deep learning methods, they operate well on regular grid data, like 2D images and videos, but they struggle with 3D scenes, and they struggle even more with 4D scenes, which is 3D things moving and deforming across time. So if we naively feed high-quality data to deep learning methods, we reconstruct motions or poses, or we synthesize them, and we see that they are imperfect. So we have lack of contact where we expect contact to take place, or we have ugly penetrations. Just to simplify things in this talk, we will talk only about 3D scenes, so we'll ignore the axis of time. Moreover, we need to model complex and fine-grained relationships between interacting shapes. Why? Because as humans, we're very sensitive even to the smallest artifact in inferred poses. To tackle strong challenges, we need strong tools, and for this, we'll build on top of a simple model. Gerard is one of the original authors, and this model looks like real people and moves like real people, and it is very easy to animate and easy to fit to data. This is important for people like me and you and our methods. However, looking at some details, the face is always neutral, unexpressive, and the hands are always open and flat. And we know that with non-articulated fingers, we can barely do anything in life. So I will skip technical details. We go back to the simple model that has no finger articulation, and we develop a hand-only model that has expressive articulation, and we extend simply by concatenating this model. It turns out that my colleagues were also working on an expressive face plus head model, so we concatenate all these things together. This is much more complicated than when it sounds. Why? So that we approximate the homunculus idea. We give higher modeling capacity to body areas the brain thinks that are important for communication or interaction. And we call this model simple X for simple expressive. And now that we have a strong model, we need to exploit this. We didn't build this just for fun. So we want to come up with some black box method that takes as input a single image, and as output, it produces a 3D configuration of this simple X model that best matches, reflects the input image. Nowadays, this is some kind of deep network, and of course, we need training data for this. The problem is that training data nowadays is kind of scarce, and not far ago, there was actually no training data for this. Luckily, there exists a solution, optimization-based methods. They need no training, so we can exploit them to collect pseudo-ground truth and build training datasets. And proxy 2D joins, they're easy to annotate and easy to detect. So what we'll do is that we'll take an off-the-shelf method, we'll estimate a 2D skeleton from the image, and now the 2D skeleton, the 2D key points, they are our observations. And our 3D model, it has an underlying 3D skeleton, so we'll estimate a virtual camera, we'll project the 3D skeleton onto the 2D image, and we'll try to match the reprojected 3D skeleton to the detected one. And we'll be changing the configuration of the model until we nail this matching. At a higher level, this method is called simplify when we fit the simple model to an image, or simplify X when we fit the simple X model to an image. And we can go ahead and apply this method on in the wild images of many different subjects. Here we see just one subject, but with various poses and various expressions, and then we can have semi-automatic methods to curate this reconstruction so that we build training datasets. And this works reasonably well. However, let me state the obvious, it focuses only on the human and it totally ignores interactions with objects. And this should not be taken lightly because we cannot just trivially extend our methods for this problem, because we face strong challenges, mainly two challenges. First, we have strong depth ambiguities. What does this mean? In this example, where we have the surfing board, we have infinite configurations of the surfboard that are further away from the human or closer to the human. You can imagine that the further away we go, also the size changes. And all these configurations result in the same projection on top of the image pixels. Moreover, we have a lot of strong ambiguities. This is a fairly simple example, but we see that the human is occluded by the table, the fork is occluded by the human, and the chair is occluded by both the human and the table, and so on and so forth. So we have terrible ambiguities, and ambiguities is a loss of information. So then, we can give up and call it a day. Or we can see this as an opportunity, and this is a source of information. Why? Because the body constrains the object, and the object constrains the body. So now we have something to solve. How do we constrain things? Through contact, because as humans, we always use contact to execute tasks, and we use hands to grasp tools and type on the phone. We use the legs and the feet for locomotion, the full body to carry big objects, and also to sit on the table while working on the laptop and eating an apple. This is a relaxing action, but this is very complicated because this involves interactions and proximal relationships with many objects. So we need to model contact appropriately and estimate it for the full body. Looking into the literature, a lot of work focuses on contact only in 2D pixel space. They ignore 3D. Or they do 3D, but they focus on the joint level and they forget about surfaces. Or they focus on the surfaces, but on a very rough patch level granularity. Or they use synthetic or scanned data, which is nice, but methods trained on this, they struggle generalizing in the wild. Instead, our goal is to get natural in the wild images and infer dense vertex level contact on the 3D surface of the full body. In this case, with blue color, we highlight the contact at the buttocks for sitting on the motorbike, but also on the hands for grasping the handles, and the feet for, changing gears or whatever these guys are doing. And we want to do this for any image taken in the wild, indoors, outdoors, more artistic photos or sports photos, and so on and so forth. And to do this, we need appropriate training data. So how do we collect this? The idea is pretty simple, and initially I didn't believe that this would work. So we have a 3D viewer, and think of this as the 3D version of Microsoft Paint. So people have a Vitruvian human, and they can rotate and zoom in, and then they can spray some binary labels on top of this. So in this case, we embed this into a browser. Okay, I don't know where my mouse is, it doesn't matter. We embed this into a browser, and we employ a lot of people on Amazon Mechanical Turk. So basically, now we will crowdsource annotations, and we show several images to these people, and then people need to paint the respective context. For example, here the laptop is resting on the laps. And we do this for all the objects that we detect with a VLM, or we ask people to annotate general scene support conduct. So we do this at scale on Amazon Mechanical Turk. Here on the left, we see several examples of images. In the middle column, we see contact labels for the specific objects. And on the right, we see general scene support conduct. So let's focus only on one example for the sake of this discussion. Here are the objects that we detect with a VLM. With a car, there's no contact for obvious reasons. But for a bicycle, we have the yellow patch at the buttocks for sitting on the saddle and contact on the right hand for grasping the handle. For the cell phone, please don't do this while driving, but we have contact on the left hand and on the ear. And interestingly, when annotators, they can confidently hallucinate occluded information, they go ahead and annotate this, for example, for the handbag. And we also have scene support contact, which is like the union of some patches that we described earlier. Now we collect this dataset at scale, and on this we train a very simple model that is based on simple principles. As humans, when we look at this picture and we want to reason about contact, we focus on three things. First, body parts. Secondly, proximity to objects, nearby objects. And third, the nearby scene context. So three things. And also our model reflects these three things with three branches. So we have one branch for body part attention, another part for scene context attention, and a cross-attention layer to basically bridge the two together. We train this on the dataset that we crowdsource, and the distribution looks pretty rich, but also heavy-tailed, because any dataset that focuses on interaction is heavy-tailed. We have rare objects and rare actions, and so on. For every image, we have binary labels. For every vertex, do we have contact? Yes or no. But by having many annotations across many images, now we can aggregate this information and normalize. So we can visualize, so we can compute contact likelihoods and visualize them across the full body. Here, this is shown with color coding. So blue means it is unlikely that I will contact anything with the outer palm, but it is very likely that I will use my fingers to grasp something, or the back of the head for sleeping, or even the mouth for eating, and the ears for listening to music and taking phone calls and so on. These are very interesting statistics, and again, let me state the obvious. Although contact is informed by objects, we have annotations only on the human body. So our dataset lacks 3D object shapes, and of course, by extension, it also lacks contact annotations on the missing object shapes. So now we have another problem to solve. First, we need to recover the missing objects for every image and their foundational models. We'll use the OpenShape foundational model that takes several modalities like 3D shapes, images, text, and so on, and it embeds everything into a single latent space. And here, with blue stars, we visualize only the embedded 3D shapes. And now in test time, I will get my input image. I will embed this into the latent space. Maybe it lives somewhere here. And then we'll evaluate distances to all other embedded data points. We'll find the nearest neighbor and we'll decode this as a 3D mesh. It is as simple as this. And assuming a rich enough database, which nowadays with Observerse and so on, it's a pretty realistic assumption. This is simple yet effective. So we go back to the previous dataset, Daemon, that pairs images only with 3D contacts on the body. And now we extend this with an object mesh that we recover per image, and also 3D contacts on the object. How do we find these 3D contact annotations on the object? Well, the obvious way is let's do the same thing that we had again. We have the 3D visualizer, so let's hire people, let's spray contacts on the objects. However, first of all, painting objects, I mean, it scales. We did this, and it is useful, but it is still tedious. Someone needs to do this, and we spend some money. But more importantly, if we separately spray contact on the body and on the object, there is no guarantee that this will match topologically. And it is very important that we have this consistency. So how do we solve for this consistency? Well, the easiest thing is let's get whatever we have on the human and let's transfer this, let's project this onto the object. And this is exactly what we'll do. So we'll start with whatever body annotations we had earlier, And first, we'll break the full contact into contact patches per body part. And then we'll do something interesting that we borrow from the graphics community. We'll parameterize every contact patch with a contact axis. This contact axis is this red geodesic curve on the mesh. But we can parameterize this with a simple vector, with a starting point and a direction. And we extend this method with some novelties so that we can apply on the human body. I will not bother you with these details. But now the interesting part is that if we want to project the full contact patch from the body to the object, now this boils down to just projecting this contact axis. So what we'll do is that we'll go ahead and we'll do only 2 clicks. 1 click for the starting point and another click to define the direction of the contact axis. And that's it. In a sense, we zip the contact area into this axis, we transfer the axis, and then we unzip the full contact area onto the object with some deformation so that it matches the surface. Interestingly, this defines dense one-to-one correspondences for contact points on the vertex level, which looks like this. So we have one-to-one correspondences between vertices of the buttocks, for example, and vertices of the saddle. Or in other words, we have unique bijective correspondences. We built on top of the DECO or Damon dataset that we introduced earlier. So the statistics look similar. Again, some kind of heavy-tailed distribution, but it is quite rich. We have 4,000 images, more than 500 object instances, 44 object classes. There are some differences with respect to the previous dataset because we do some curation, but I will not bother you with this. You can go to the project website, and the dataset is coming soon, within the next 2 weeks, before CVPR. But we already have a dataset exploration webpage, so you can go there, and there is a drop-down menu, so you can choose your favorite category, like chairs or couches, and so on. And you can see contact on the body, the corresponding contact patches onto the object. And we do this for the suitcase, for example, for grasping the handle or drinking tea. And you can see contact for the mouth with blue and contact with the fingers with red, even like contact with the pinky in this case. Grasping a fork, eating an apple, and so on. And after collecting all these annotations, well, we need to exploit these annotations. Otherwise, what's the point? So we have a fitting method that takes meshes and it fits the meshes into the image. We have 2 versions of this method. We call this PICO-fit. The first method is denoted with the red star. So given an image with an off-the-shelf method, we'll reconstruct this human shape and pose that we see with blue color. And then for images that belong to our dataset, this is what the star denotes, we will simply load our pseudo-ground truth annotations so that we exploit them. So we load the object shape. We also load the correspondences between the human and the object. And now we have an optimization-based method that snaps the human onto the object while keeping some pixel losses happy. And for images that don't belong into our dataset, therefore we don't have pseudo-ground truth annotations for this, we'll infer a human body in the same way, but we will also detect 3D contacts onto the body with the regressor that we introduced earlier with DECO. And we don't have pseudo-ground truth annotations, so now we will use the contact onto the body as a key for database retrieval, because these regressions, they're going into the right direction, but they are not perfect. So for a given object class, using as key the 3D human contact, we will find into our dataset the closest 3D human contact, and then we will also recover the corresponding contact onto the object and the object mesh. So now we can use all these things into an optimization-based framework for reconstruction. At this point, we have initialized the blue body, shape, and pose, and only the shape for the object. So in the first optimization stage, we use the contact correspondences to snap the object onto the body, but these don't align with the pixels. So in the second stage, we keep the blue guy fixed, and we refine the pose of the object so that we keep pixel losses happy. And then we keep the object fixed, and we refine the blue body so that, again, we improve contacts while keeping pixel losses happy. This will make more sense visually. So these are our input images. Body regressors nowadays, they are very reasonable, but initializing the object is quite off, so you see very wrong orientations. In the second stage, we keep the body fixed and we refine the object so that now the object aligns on top of the right pixels, but we still have some missing contact. So now we keep the object fixed and we refine the blue guy so that we have nice contacts while also aligning to pixels. And this works well for several examples. These are PICO-fit star results for riding a motorbike, resting on a bench, having dinner, enjoying the sunset, playing tennis, and so on. We have a comparison with the state of the art. References will follow in the next slide. We compare against Conto, HDM, and FOSA. Sometimes we give some privilege to ground truth for competitors. And I will not bother you with details, but competing methods, sometimes they infer only point clouds instead of meshes, or they have missing contacts, or they have penetrations. Our method generally performs better. It's not perfect, but it goes into the right direction. And we want to tackle in the wild scenario. So how the hell do we evaluate in the wild? I believe we will be seeing more and more of perceptual studies in computer vision. Up to now, this was more of a thing for synthesis. So we have a perceptual study and we compare our method and several competitors against our PICO-fit star that has access to ground truth. And of course, people perform this PICO-fit star method because it gives state-of-the-art results and it uses ground truth. But the second best performer is our method that has no access to ground truth. So at this point, probably I convinced you that collecting 3D contact annotations, it scales and it is useful. However, no matter what, annotations will always be finite and they cost something. After our work, they cost mainly time than money. The question is, how do we go beyond annotations? So enter foundational models. How will we do this? Let's start with an image as input. And we feed this image to a lava model that we also fine-tune with LoRa on interaction datasets because lava is originally for segmentation. And these guys, they will produce contact reasoning tokens. And then I can use these tokens for whatever I want, to guide whatever I want. So I will use this for a foundational localization model so that I can localize contact somewhere. This is a Lisa model, for which you can think of as a language-guided sum model. And this was originally developed for segmentation on 2D images, which is exactly the problem. We care about a 3D problem, but these work only in 2D. So we need to tackle this fundamental limitation. And the nugget for resolving this is what we call render localize lift, RLL for short. This is a very simple idea, but effective. So what we'll do is the following. We'll get a Vitruvian human. It doesn't matter if it is simple or simple X. This is model agnostic. And we'll also get a canonical object mesh that we recover with the database retrieval that we discussed earlier for this image. And then we'll use synthetic virtual cameras to render multi-view images for these guys. Now, please remember that we have perfect knowledge of these cameras. So maybe we'll need to exploit this later. Then we embed these images into a share encoder. And we have two decoders, one for the human, one for the object. And these decoders, they are guided by the tokens that our VLM generated earlier. So we have this SAM-like model that is guided by the interaction tokens. And after detecting contact in 2D, these are two-dimensional masks, now we can lift them in 3D. How? Well, please remember we had knowledge, perfect knowledge of the cameras. So now I can get any 2D point and I can triangulate this to exact 3D points. So problem solved, right? I detected things in 2D, so I lift them in 3D. This is what I care about. Problem is that SAM is not multi-view aware. What the hell does it mean? It means that 2D contacts across views, they don't necessarily agree with each other. So we have a new problem to solve. How will we do this? With two very simple steps. So first, let's focus on this bottom area. We'll introduce this face lifting module that takes information from the cameras and it transforms the interaction tokens so that they are aware of the multi-view information. And then whatever 3D contact I have lifted, well, we'll have a very simple loss on 3D ground truth contact so that we encourage this consistency. Very short recap without the details. We have an image, it goes through a VLM to get interaction tokens. These operate only in 2D. So we'll get some meshes, we will render multi-view images, and then we will localize contact in 2D and lift this in 3D. Some qualitative results, we observe that all the methods, they detect binary contact, yes or no, for any object. It doesn't matter what the object is. But in real life, we interact with multiple objects. So we introduce a new task called semantic contact detection. And now we see that conditioned on the object label, we have a very different contact estimation for the same image. So these are some results for lying on a bed while working on the laptop. The contact is highlighted with red. Or walking with a handbag and holding an umbrella. Having dinner, so contact mainly on the hands. And taking a selfie with a phone while having a handbag. We also compare to the previous method that we introduced earlier, and we extend this for this new semantic contact task. And we see that just using 3D annotations, models trained on these, they have a lot of false positives and false negatives, while exploiting the knowledge of VLMs, it gives us robustness. And I have to admit, I rarely get excited with plots. Usually I like visual results, but with this plot, I got super excited. So what we compare is the DECO baseline that we introduced earlier. It uses only 3D contact annotations, and with blue, we see the Interact VLM model that also exploits VLMs. And on the x-axis, we see the amount of 3D annotations that we use for Interact VLM. DECO always remains the same, but our model uses 1% of the 3D annotations, or 10%, or 100%. And we see that with less than 5% of the training annotations, because we exploit the VLM, our new model already beats the state of the art. And when we add 3D annotations, basically it kind of skyrockets, and adding annotations, it never hurts. By the way, here we have a jump because we have a heavy-tailed distribution. So after 75%, we sample all the rare cases, and then the model gets happier. It gets much better. So this Interact VLM model, it minimizes reliance on 3D data. And don't get me wrong, we should still be using the 3D annotations. We should still be exploiting them, but we can go well beyond this to build much stronger models. We can also detect contact onto the object. We will not stay long into this, because eventually we want to exploit this for reconstruction. This is what we care about. So what we'll do is that we'll get this image. We get a Vitruvian human, we retrieve this object, we estimate the 3D contacts on this, and now I want to do 3D reconstruction. And please note, this is a dummy initialization. I initialize with contact annotations, but the object is quite off. So with simple render and compare, this is quite effective. A very simple method can have state-of-the-art results. We compare against some state-of-the-art methods. On the right, you see our model. On the left, you see a state-of-the-art method. So we have a lot of missing contacts, and they can tackle limited classes. And here are more results of our method for frisbee, baseball, some sports sequences while having a backpack or holding a bike, or everyday photos like this. Fine. So at this point, we know how to do 3D contact estimation in the wild, and also do state-of-the-art 3D reconstruction for interactions. However, for getting the object shape, we are kind of stuck with object retrieval. And don't get me wrong, this is simple and useful, but why not recover any object shape, even under strong occlusions that are very typical for interactions? And to tackle this, we get inspiration from the simplify method that we introduced earlier. And simplify-like methods, they have been a catalyst for the community. Why? Because they help us collect pseudo ground truth annotations for training whatever we want to train. And at the heart of this lies a generative, explicit generative 3D model, which is the simple body model. In that sense, we generate hypotheses with our model, and we compare the hypothesis to the image until we get a nice reconstruction. So in a sense, this functions as a strong 3D shape prior. What does this mean? If we have some occluder hiding important information from the body, just by looking at the visible information of the human, we would still be able to recover more or less the same reconstruction for the body. And to me, this is a little bit of a mystery. I'm not sure why we still do not have such a generative 3D model for objects and such a fitting method for objects. So the question that we like to pose is, what is a simple, generative model for objects? And what is a simplified reconstruction method for objects? To answer this, we need to compare bodies and objects so that we understand the needs. And for bodies, we talk about a single class, while for objects, we talk about basically infinite classes, like chairs and sofas and cars and you name it. This means that the shape variance for objects, it is only intra-class, while for objects, it is both intra and interclass. So it is much wider. It's a more difficult problem. For bodies, we have a fixed topology. Simple X has the same triangle connectivity for all identities, while for objects, we have a wildly arbitrary topology. A chair can have one leg or three legs or four legs or you name it. And for key points, so that we also establish 2D to 3D correspondences, for bodies, we have very robust methods. They always work reasonably. For objects, there's a lot of research on this, but still up to date, I don't know something that I can download, and it always works for any image and so on. So long story short, answering these questions is non-trivial, but at least our observations will point the direction to which we need to go. So when we think about many classes and the huge shape variance, we observe that nowadays we have rich databases because we anyway exploited them for retrieval. But we also have robust detectors and classifiers, some like methods. We conclude that maybe it makes sense, in practical sense, to have category level models for robustness, because we can detect the class. When it comes to the topology, we observe that nowadays as a community, we've done leaps of progress for deep implicit shape modeling. And these models, they have a latent space that we can traverse. And in a sense, we kind of smoothly, morph an initial shape so that we can grow armrests, for example. So we conclude that our generative model can be a morphable SDF or MSDF model. And when it comes to correspondences, we observe that nowadays we have foundational image models that pull rich features from images. And by rendering multiple views of 3D meshes, we can do the same thing for 3D meshes as well, so that we can establish 2D to 3D correspondences with simple tools. We'll see this again later. But we conclude that we can exploit deep features. So let's start building a solution. Our generative model will be an MSDF, morphable sign distance function. So, and without reinventing the wheel, we get something from the literature. This is called the DIT model. And we see some examples for the sofa space, airplane space, and car space. And the DIT model has three nice properties. First, it has a template per class. This is the central shape. Then it has a compact latent space, which makes our search space easy to work with. And we can traverse this so that we generate multiple different variations of this sofa. And please note also the color coding. While we morph our shape, we still have semantic correspondences. The same corner is shown with yellow color across all these morphed shapes. So fine, this will be the heart of our method. So now let's start building our framework. This is the input image, and my observations will be some intermediate feature maps that we estimate, like masks and normals and depth and so on. Then we have the generative model that helps us generate hypotheses. And then I will render and compare the hypothesis with the visual observations. And I will change the hypothesis until these guys look very similar to each other. And then I will call it a day, and this will be the final reconstruction. When it works really well, but this is optimization-based method. So this is prone to local minima. This is natural, which means we need a good initialization for both shape and pose. How do we initialize shape? We'll do exactly what we discussed earlier, no new information. So we'll do this database retrieval, but at the last step, I will not retrieve the nearest neighbor as a mesh, but as a morphable SDF code, so that I can also refine this. And how do we initialize pose? From the input image, we will pull rich foundational features, stable diffusion and dyno. And for the mesh, for the MSDF, we will use multiple synthetic cameras, we will render views, we will find in every view foundational features, and then we will back project them back to our 3D shape hypothesis, and we will aggregate this information. So now we have 2D features, 3D features, so you can imagine we can find some initial correspondences. Of course, they're noisy. So then with some camera and with Ranjak and PNV, like standard traditional things, we can keep only the inliers and while solving for pose. And this is not perfect, but when it works, it brings us into the right ballpark. So we go back into the render and compare framework and we plug our initialization and we are good to go. So we see some results for chairs, for sofas, for airplanes, and for cars. And I have more classes, but I ran out of time. We have a comparison against the state of the art, and at least back then we thought that zero shape is the state of the art. For clean images and common poses, this method gives very nice results. But for uncommon poses, we see that they struggle reconstructing occluded parts. While our method, it always gives reasonable occluded parts. Why is this the case? We think this is the case for 2 reasons. First, because our method has an explicit 3D shape prior. And in a sense, this looks old-fashioned, but this is like rock and roll. It never dies. And we also have a feedback loop. So if we have errors, we have opportunities to refine for these errors. While while state-of-the-art methods, they are feed-forward networks. They give something in one go, and they don't have opportunities to correct for errors. And they have only an implicit 3D shape prior in the network weights. And networks, sometimes they freak out and explode. So our method is nice for occlusions, and we have a more systematic evaluation under occlusions. And to this end, we borrow this idea from the human literature. So we have a synthetic occluder, and we have full control so that we randomize the position of this patch and the size of this patch. And we have this plot where the x-axis shows the amount of occlusions. We have less occlusions or very strong occlusions. And the y-axis is the error of the reconstructed shape. The lower, the better. We see that with orange that our method is pretty stable even for very strong occlusions. This is the average and this is the standard deviation. While the state of the art, it is roughly on par for no occlusions, maybe even a little bit better, I don't know. But even for small occlusions, it quickly gets worse and much worse, and then at some point it freaks out and explodes, and that's why you see a huge standard deviation for strong occlusions. When the method works, these are some qualitative results, like reasonable reconstructions under relatively strong occlusions. But some people think that these occlusions, they are not realistic, right? Because in the end of the day, it's a stupid rectangle on the image. We have evaluation on hand object graphs, but I will not show this. What is a little bit more interesting is I have just qualitative results. So these are some reconstructions for COCO images taken in the wild, and we have like strong interactions and strong occlusions by the body. And to give some privilege to our baselines, we also in-paint the occluded pixels so that we remove ambiguities. So we compare against zero shape and against stripe OSR, which is a more recent method. It is thought of like being stronger. We see that in painting, it always improves the baselines. But consistently, our method performs better because it has this feedback loop to correct for errors, and it has an explicit 3D shape prior. I think I ran out of time. So at this point, we know how to reconstruct objects, but these objects are in isolation, and we can use these objects either in the methods that I introduced earlier, or we can go ahead and do something different. We can generate an interacting human that grasps these objects, either for visual reality applications or to generate synthetic images with perfect ground truth. So I will skip details. You can go on our website and have a look at this. At the heart of the method lies controllable generation. So given a desired 3D vector, we can generate hand-only grasps that have a palm direction that satisfies the vector, or a reaching body that have an arm that satisfies this direction. So this gives us controllability. So that we can grasp an object only from a direction that is plausible. And how do we do this? Simple ray shooting and simple collision check so that we find the directions from which a body can actually approach the object without penetrating. And here just some results. I will not bother you much. We have pretty realistic synthesis results for various object shapes, but also object placements. So this is medium height position, where the object lies somewhere between the knee height and the chest height, or big height position, where the body needs to stretch up, low height positions, where the guy needs to bend down. It works for right hand grasps, but also left hand grasps, and okay, perceptual studies and whatever, I will not bother you. So at this point, we have discussed about methods to estimate body contact, body plus object contact by crowdsourcing annotations. We have gone beyond contact annotations to exploit VLMs. We reconstructed objects and we synthesized grasps. If you're interested in any of these works, you can go ahead and visit our project websites. The code and the data is always public for published methods. CVPR papers, they are coming within the next 2 weeks. And these are all my collaborators. And yeah, with this, I would like to thank you for your attention.
Is there any questions? I think we can take one question. Oh, here. Just for the recording.
Hi, thanks, Dimitris, for the nice talk. I have a question about this deep SDF kind of model that you trained. Do you observe problems in the latent space when you optimize, like being non-continuous or things like that? Because in our experience, the problem with these models is that because the latent space is not very continuous, when you optimize, you end up with places where leads to no shape, and then it's really bad for optimization. In that sense, it's very different than optimizing the latent space of simple. So
yeah, this is a very good question. So we were very conscious of this thing. So we tested this out. So interestingly, in the object community, because they care about different problems, they don't care about this continuity. So there might be, for example, like isolated islands in the latent space, or it could be that different places in the latent space, they have kind of similar objects. The problem is not crazy, but people train networks without incentivizing for what you say. They don't incentivize for continuity and for not having duplicate thingies. So long story short, yes, there is a small problem. I think the problem is not terrible, but there is a problem. And we just need to be aware of this so that future versions of this, they tackle this. But for doing early steps, I believe that we don't really need this. Why? Because if the shape initialization is good enough, then you do only local search, right? So even if you are on some isolated island, if the island is nice and fancy, sunny, then you can stay on this island for a while. And you do just local optimization. So, I mean, it's okay. We can do useful things with what we have. But yes, this is a good observation, and that's a good problem to solve.
Maybe we can take one more question. Otherwise, let's thank the speaker. And